All right. So this is a sinusoidal signal, and the period can be taken from peak to peak. The period is 2 pi omega. Okay, 2 pi omega. Okay, theta for xt is a cosine omega t plus theta. Okay, this theta can be, this is a cosine. The theta can be a deviation, maybe it's from here. Okay, maybe a theta, maybe I'll draw it here. It's a theta. This theta, we are assuming this is cosine because usually cosine starts here, right? Usually cosine starts here. Now it has moved from here. It has moved from here to this spot here. So there's a phase shift, and this phase shift is theta. This phase shift is theta. It can be plus or minus. If you are moving to the right, then theta is positive. If you are moving to the left, then theta is negative. Okay, so xt is omega t plus theta. So in this case, since you are moving to the right, omega t, so inside it has to be plus or minus, isn't it? Am I right?
Yes, sir.
Yes, sir.
Inside has to be minus. So because the way you look at it, when will be cosine theta 1? When will be when is cosine omega t minus theta is equals to 1? When omega t minus theta is equal to 0, right? Okay,
Yes.
when omega t minus theta is 0, you get cosine omega t minus theta is equal to 1. In that case, if we solve for omega t is theta. So that's what it's telling you here. In this case, when omega t is theta, you're going to get a cosine 0 is equals to a, right? So this is the a we are talking about. It has shifted. The maximum point has shifted by a. Sorry, the maximum point has shifted by theta to the right. So that's how you look at it. Do you guys follow?
Yes, sir.
Yes, sir.
Any question here?
Yes, sir. No, sir.
Okay, later on I will be giving you some examples. Remember, for the other guys, the January semester 2020, I was doing the midterm review that day. We had some problems like this. So let me define everything. A is amplitude. Let's say if you go for an interview, and if you don't know even the basic equation for a sinusoidal waveform, then the employer going to be very mad. Let's say you're going for an, okay, we'll, so omega is angular frequency. Okay, anyway, I don't want to talk nonsense like I used to do in the class, because there we had time, now we are online time. So let me move quickly as fast as possible, so that, because I'm sure you guys are also very busy, right? In radians. Period. In seconds. In hertz. Okay, is it clear? So
Yes,
you can,
sir.
okay, this is a sine wave in time domain. Then now I want to present this waveform in phasor. You guys might have familiar with phasor from your power class, right? I don't know if you might have some understanding, but again, I want to go through here how this time domain relates to phasor. Okay, this is your time domain, for example, and then you have time axis, right? But here in the phasor, we don't have time axis. It's amplitude. It's basically, it's not time here. It's amplitude, maximum amplitude. It's amplitude axis, but there's actually so okay, when that's maximum amplitude in cosine, maximum amplitude is A. Okay, maximum amplitude A. Okay. Let's say right now your phasor is at this point here. At this point. Phasor, let's say A theta. Phasor is something, a signal that is represented in the form of amplitude and phase. Phasor starting at t equal to 0. Okay, when time t equal to 0. And again, somebody messing with the mic, I don't know what's going on. Has anybody got a question?
No, sir.
Are you doing that, G?
No, sir. I didn't do.
Usually theta plus omega t, right? Right or not? But if your time is 0, if you're starting at 0, then we're starting at time 0, then just theta, right? after some time, let's say this phasor has moved to here. For your information, phasor rotates counterclockwise in angular speed. The phasor got angular speed is rotating counterclockwise. After some time, the phasor has moved to the phasor okay. It has moved after some time. So there is a phase involved right now. The phase is just a distance travel, angular distance. Okay. So at any time, let's say if I drop a line here, or maybe I go back to red. If I drop a line here, and this is your xt. Sorry, there's no xt here because this is phasor. Okay, that's your xt. Your xt, when you drop a line here, so your xt is going to be, xt is going to be a cosine theta. Be a cosine omega t plus theta. So when you drop a line on this axis, so it's going to be a sine. Okay, so that's how you look at you have in time domain, and then you also can represent this information in phasor. Phasor is a rotating vector. As it rotates, it's going to trace the sine wave or cosine wave. Any question on this?
So far, so good, sir.
Okay. Next, we look at the Euler identity. Euler identity will be talking about this quite often. Just Euler identity alpha. You can just put theta or beta, it doesn't matter, but it's just telling you e to the power of j alpha is cosine alpha plus j sine alpha. The Euler identity. Cosine alpha is e to the j So there's these are some useful identities that becomes handy when we are solving problems sometimes. So you can see the difference between sine and cosine is you have j here. For sine, you have j here, but there's no j here for cosine. And then you have a minus sign here, but there's a plus sign here. These are the things. It's one way that you can remember. Sinusoid in exponential form. Xt is equals to cosine xt is a cosine omega t plus theta. Using the Euler identity, using the Euler formula or Euler identity, I can write this as a okay, there's some kind of a echo or noise is starting. Is somebody doing something? Please stop it. Now we can break up the exponents. You can write the above exponential function as e to the j omega t times by e to the j theta. Similarly, on this side, you can write this one as e to the minus j omega t multiplied by e to the j theta minus theta. So you have to be careful about where you write your a. The a is not multiplied to, the a is multiplied to the old term. The a should be here, or you can just put a parenthesis to indicate. After doing this, what we can do is we can separate the constant part from the variable part. Can separate the This is T. A over 2 E j theta E j omega t plus A over 2 j okay. I'm just multiplying the A through, and then I separate the exponents. So in that way, you know that this part here, you can call this, this is a constant. You just call this D. And this part also is constant. Okay, the only difference between this D and this D, this is also, I can call this D asterisk. The reason I'm calling using D asterisk is because of this, because of the conjugate, because of it's a negative sign here. So the imaginary part has a negative sign. So this is D, and therefore this is the D's conjugate. Conjugate. Any questions so far?
No, sir.
No,
How about that? Good. Are you sure? If anybody have questions, please ask now. Or if you want to look at the video again, and you can also ask later. Okay, then let us continue. Therefore, I can write this. It's a very good, it should be, the reason we are doing phasor is because later on when you go to Fourier, of course we have done enough Fourier, so you can see clearly where these things come from. D e to the j omega t plus the d conjugate e to the minus j omega t. So I can write this in a compact form. So this part here is a constant. And this part also. This part here is a function of time. Similarly here, function of time. Any questions so far?
No.
Just to, yeah, okay. So next time when you look at things like this, you know where this constant part come from. You see the constant part is due to the phase. The phase shift is constant. But this part, e to the j omega t is not constant because time is varying. Omega is constant. The rotating speed is constant. But time is not constant. Is time constant? Time is changing. Right now, as you sit there and watch this video, time is moving. Time never stops. But they say you can stop time and space. If you do that, then you become sane. Okay, you'll think about that at the end of your life, you know, maybe after you're done with everything. Okay, now let's move on to the generalized expression for sinusoid. General expression for sinusoid is equals to xt is a. Now we have, remember earlier on you just had cosine omega t plus theta, right? Now to make it complete, you must have this term here. Okay, what this term will do, it will tell you a few things. This term can make your system go unstable, can make it go stable. So we look if theta, if sigma is less than 0, then what will happen to the sinusoid? If sigma is less than 0, that means if sigma is negative, you know, negative. Let's say example, sigma is e to the minus. So in this case, you're going to get a decaying sinusoid. So let me just draw it here. So it's going to be like decaying, decaying. I don't have clean ends. That's why the sinusoid is not coming out right. Well, okay, something like that, you know, not really good. I don't really like this drawing, but it's okay. So the e to the minus sigma t is responsible for the damping effect of the sinusoid. If sigma is greater than 0, for example, if its exponent part is positive, then signal is going to grow. You know, it's going to grow unbounded. So this is not a stable signal. Let's say if this is what happens during the tsunami wave. The virus, luckily virus is not going this way. We can see like, you know, this is growing. It also has an envelope. The one that's drawn in red is called the envelope. So now the coronavirus, since we are here, just to tell you why signaling system is very important. In coronavirus, they're also using an equation to predict the growth factor. Somebody predicted the growth factor and they estimated. So once, let's say it's growing, right? And something is growing like this, and then they, from this slope here, they can determine a growth factor. For coronavirus, the growth is not exponential. It's something like A is equals to B C X, something like that. So if you can determine the initial value, and then if you can determine the growth factor, and this is the number of days, and then you can predict the future. Somebody predicted the American number of new cases quite accurately. So you see now, signal and systems, they are also applied to other things. If you are really good in this type of analysis, you can make a lot of money, analyze and forecast economy, and then you know what to do. Some people know when to buy and sell stocks. But anyway, if sigma is 0, then you're going to get a steady state. Steady states okay. Any questions so far? But don't be scared to ask question, please. We don't want to go very fast and don't learn anything. We just want to go slow. And then learn.
Sir, what's the sigma stand for?
Sigma is the damping factor. It's the real part. The sigma is included here to show you that if the signal, if is sigma is like in the if you talk about in the real electrical circuit system, like in electrical engineering, then let's say you have an inductor, sorry, capacitor. Let's say if you derive the equation across the capacitor, let's say if you derive the equation voltage across the capacitor, eventually you will see the voltage across the capacitor, let's say I'm telling no, e to the minus RC. This is C, right? This is R, C. So like if you R over C or RC, I'm not sure. Okay, I think it's RC. And you see the resistor R can determine the decay. So this is a more like in electrical circuit, this is related to sigma. Related to sigma, you know, because resistor dissipate heat, right?
Yes, sir.
Resistor dissipate heat. So therefore, for a real system, we should include sigma for losses in the circuit. Not only that, we also include sigma to study if the circuit go unstable, and then sigma also can tell, it can be used to model the circuit.
Okay,
I don't know if I answered.
Got
Okay.
it, sir.
Okay. Later on, when you studied electrical circuit, actually, there are some people even teach electrical circuit in signal and systems to show, because if I bring in electrical circuits here, students will suffer. But we can show one or two examples later on how the sigma comes about. So now I can show you in exponential form, xt in exponential form, xt in exponential form. Then you can see where the sigma falls. Xt in exponential form is e to the, now you include, earlier on, we already had this equation, right? D j omega t d asterisk e to the j minus j omega t. Okay, this is equation that came from this derivation. You remember, this equation is just for the sinusoid, right? This equation is just for the sinusoidal part. Now we try to look at this equation again, including now we derive this equation with e to the power of omega t. Now we are making the equation more realistic. Because all signal, in any circuit, there's dissipation. In your iPhone or iPad, you have to charge again. There are losses. That's what the sigma represents. This is one of the things that the sigma represents. So let's include this now and see how it affects the sinusoid. So you multiply the e to the j, you multiply through the exponential function, and then you'll end up getting something like this, e to now we combine the exponential part. It's a real part, sigma is the real part, and then the omega is the imaginary part. Okay. And then next what we do, we define. We call this part here S. Call this S. We call this part here S. And then call this the conjugate part, because it's on one side you have positive j omega, on the other one you have minus j omega. So once S on this side, and this side is S asterisk, indicating complex conjugate. Okay, then we can try to define now your xt becomes d e st so that's how compactly. So now you can see this clearly as what S really is. S stands for complex frequency. in Laplace transform, you use, right, Laplace. In Fourier series, S is just j omega. We assume in Fourier series, sigma is 0. So things can be, so the Fourier series analysis is in steady state. Any questions?
No,
No,
sir.
sir.
Now we look at energy and power signals. We look at energy and power in the signals. Do you guys want a short break for 5 minutes? You want to grab a drink or anything? Feel free. Or you have everything on your table. Okay, before we get there, we just want to say a few more things. In general, real exponential signals. Just now we just looked at a complex exponential signal, right? These are the complex exponential signal. I mean, this is the complex exponential signal because it has both a real and imaginary part. The signal, the frequency becomes complex when it's decaying. The real part makes it decay, but the frequency is still maintained. The frequency, I mean, the period frequency is still conserved. Maybe, I don't know about that, but they call this damping frequency. When something is decaying, so that's why in the Laplace transform, we call this omegas of B, the damping frequency. Let's quickly look at the real exponential signals. Xt is simply e to the power of sigma t. If sigma is greater than 0, that means if sigma is e to the power of sigma t, then you're going to get a signal that's going to be simply growing like this, okay? A growing signal. There's no oscillation. Oscillation comes only when there's sinusoidal things. When sigma is less than 0, then you're going to get a decay. going to be decaying like this. Of course, you know, when t is equal to 0, this is 1. When t is equal to 0, you're here. You are here. Let's say if this is A and this is A, then it's going to be A here. Any questions before I move on? Later on, I'm going to upload a book. I'm going to upload a few books for reference. There are more examples in this book. You can practice. Actually, I'm taking some of the notes from this book. You never know, I might take some question from you also. Energy and power signals. Let's say you have a resistor, for example. Say you have a resistor R, and then you also have a voltage across it. Okay. Voltage across the resistor, and then it's also producing a current IT. You know, the instantaneous power how to pronounce instantaneous, instantaneous,
OUS.
OUS, okay. Instantaneous power PT. You know, for instantaneous, usually have a lowercase p. Instantaneous, you know, right, the difference between instantaneous and average. Instantaneous power is you just calculate the power at that particular time. You maybe can calculate power for a period or something, but you don't average it. You don't divide by the period. Okay, so this is going to be just VT. Power is VI squared. V times I. Power is voltage times current, right? Power is voltage times current. Power per ohm. Okay, this is instantaneous power per ohms. Per ohms. Per resistor. So power is V times IT per ohm. So we have to divide by the resistance. Since you know that VT is also IT. RT. IT RT, and then IT divided by, sorry, VT is equals to ITR, right? Then multiply by IT. These R's cancel, so you end up getting IT squared. I is a function of T squared. So the total energy I squared. So the energy is the integral from minus infinity to positive infinity, I squared T dt. Because energy is what? Usually energy is the integral of power, isn't it? Integral of power dt. Because you already know that we already determined the power is I squared T. So instead of putting power, we just put I squared T on per ohm basis. Do you guys clear with this? Anyway, that's the
Yes.
reason. That's the reason for having integrating just I squared T. So the unit is usually in joules. So the average power P is going to be a limit as T goes to infinity. 1 over T integrate that over a period So what you're doing, you are just integrating the instantaneous power, which is I squared T, to get the average power. So you don't need to derive all these things. I'm just telling you where these formulas come from. Okay, for arbitrary continuous time signal, for in arbitrary I just put CT, continuous time. Just put CT for an arbitrary continuous time signal. XT the normalized energy content of the signal xt is defined as now you see the difference. You have to put the absolute value squared dt. The normalized power the normalized average power is defined as P is equals to the integral of 1 over T, integral of 1 over T over a period as T goes to infinity. As the limit as T goes to infinity. So as far as one of them for energy, the integral is from minus infinity to positive infinity. For power, the integral is from over a period, and then you also divide by the period as the limit, as the period limit T goes to infinity. Later on, we'll be doing some examples.
Sir, I have a question, sir. Can you scroll up a bit?
Okay.
Scroll up. More a bit, sir. Until the instantaneous power over there.
Okay, yeah.
Yeah. Suppose the general formula for the power is voltage times current only. Am I right? Not current times, well, current multiply current divided by resistance. Suppose
say that again. This one, yeah.
Supposed to be the power formula is current multiplied by current only, right? Voltage multiply current.
Power.
Minus.
You mean power?
Yeah.
Power formula.
Yeah.
Power formula is voltage times current.
Yeah, but you wrote as power times current over resistance.
But yeah.
Yeah.
Yeah, this is voltage times current.
But why you divided by resistance?
Because this is per ohm basis.
Oh, okay.
Per ohm means it be per ohms in this case. Be just normalizing something like power per ohm. This is like something to show that when you calculate the power, and this is maybe a method of calculation. If I don't put per ohm, then you don't put the R.
Okay, sir, go ahead, sir.
Because maybe they have done this so that to simplify calculation. If they don't do this, the R don't cancel. So the R won't cancel. The simplifying calculation. Otherwise, if you don't do this, then the R will be hanging around all over the place. After you find the answer, they multiply by R to get back there. This is something like per unit calculation. Maybe you have also studied in power system, right? When they do per unit calculation.
Okay, sir, got it, sir. Thank you, sir.
Okay, welcome. So any other questions?
No, sir.
Okay. Similarly, do you guys have other class after this?
11 o'clock, sir.
Okay. What class? Similarly, for a discrete time signal, Xn, the normalized energy content of Xn is defined as this for discrete signal. Earlier on, we were doing for continuous, this is continuous, and this is for like discrete signals. Discrete. Discrete signal, we don't integrate. We do the summation. When when things are not continuous, you cannot integrate, right? So for discrete signals, we do summation in place of integral. The normalized average power P of Xn is defined as we haven't talked about very much about discrete signals. Later on when we do, and then this formula will make sense to you. Right now, I'm just giving you the formulas. Based on definition, and based on the definitions given above, it applies for all the signals, whether it's a discrete time signal or continuous time signal. If you calculate the energy signal, if you calculate the energy signal, and then if you get an energy value that's between infinity but is greater than 0, if you get a positive finite value, then it's energy signal. If and power is 0, average power is 0. Power signal, if you get an average power that's between between 0 and infinity, for energy signal, you must get a finite value, then power will be 0. For power signal, you must get a power that's finite value. In that case, energy will be infinity. You can just make the statement, or you can calculate and prove yourself. When you get a finite value for power, just for example, if you get a finite value for power, then if you calculate the energy, it will give you infinity. Later, we'll do some examples to show you this. let's say if you calculate the energy and the power of the signal, if none of them give you a finite value, then they are neither energy or power signal. These are just mathematical things right now. As you maybe work as a signals and system engineer, and then you will know what is the significance of this result. Maybe we can do some examples. Okay, since we are studying without break, so I will try to stop in like in around, maybe we'll just do one more example. We'll try to stop at 9:45.
Okay, sir.
That's fair, isn't it? Because you guys have been studying without any break. Let's do some examples on energy and power signal. If you guys have a pencil and paper, maybe you want to try to use that formula and figure out if this is an energy or power signal. Okay, I'll just give you 5 minutes. Using this formula, calculate this integral and see if you get a finite value. Can you do that? By the
Yes,
way,
sir.
Yes, sir.
by the way, I'll just give you more information about this signal. First, you must understand the domain of the time domain. You have to understand the signal. So this signal is going like this, right? E to the minus t, isn't it? If you multiply like this is e to the minus infinity to positive infinity, and then it's going to be e to the minus 2t, right or not? So e to the minus 2t okay, but because of the absolute value, then you're going to have because of the absolute value sign, you're going to have this on this side also. You under technically speaking, let me draw this complete. If you draw this, if you don't know how to draw this, then you can put a small table here. Then you vary the t. You can vary the t and then see how it, where is it appearing. So when t equal to 0, you can start plotting points. T is equal to 0, 1, and 2, and so forth. This is 1. This is 1 over e squared. So that's how we get this point here. But here, so what about when you do this? E to the negative 2t, t is equals to 0, minus 1, minus 2. There's 1, e squared, e4. So how are we going to sketch this? Maybe let me resketch this. The reason for sketching is to ensure that the signal also exists on the other side. Maybe it's doing this, I don't know. I don't know. Something like this.
Yes, sir, correct.
Then you integrate this. Since it's going from minus infinity to positive infinity, you can break up the integral. You can break up the integral from a minus infinity to 0 plus integrate Who forgot how to integrate?
Sir, well, I just replot the graph in decimal place and the is. Can you check if my graph is correct? I show in the.
Okay, sure. Okay, anyway, the graph is not important here. The graph is exists on the left and right hand side, right?
Yeah, but it's like very weird.
Because I cannot see, I don't know how to see it here, but it's okay. What is important now, should be able to integrate this. Let's integrate this e to the minus 2t divided by the derivative of the exponent, right? Minus 2 going from minus infinity to 0 plus e to the minus 2t just to ensure that signal also exists on the other side. Upper limit e to the power of 0 minus, if you plug in minus 2. Some people have a problem with these things, so that's why I'm doing it in detail. Minus 1/2 upper limit minus the lower limit. One minus 2 multiplied by minus infinity is also an infinity. Times by infinity is minus infinity, minus 1. One minus e to the power of infinity is also infinity. E to the minus infinity is 1 over e to the power of infinity one minus infinity is definitely is going to be minus infinity, right? Infinity is bigger. One over e to the power of infinity is also infinity. This is what called, I'm showing this in detail. Next time you should be able to do this. So minus half multiplied by minus infinity minus 1/2. 1 over infinity is 0 minus 1. So again get minus infinity minus 1/2 times by 0 is 0, minus 1/2 multiplied by minus 1 is plus 1/2. And of course, you know that this is going to be infinity. So you have an energy that's infinity. Okay. So is this an energy signal? To qualify for energy signal, E must be in between 0 and infinity, some number, some finite number. So now, since E is infinity, E must be less than infinity or more than 0. It must be a positive finite number, right? So since E is infinity, so this is not an energy signal. Okay, guys, I will let you go. It's already almost 9:50. We will do more examples the next time.
Okay, sir.
What do you say?
Okay, sir.
Okay, sir.
Okay, next.